Cool. Let's get going. So today we are going to talk about something that's going to become eventually very important when you apply machine learning methods. Two things, and that's how we do inference in these methods. So I thought, right, there we go. Thought I'll start with an example. So, or a slightly different way of motivating this. So let's say you've written this piece of code, or even more likely, you've been given a piece of code, and now you're about as good mathematicians as I am. So then you look at these three lines, what it's doing with res, and you're like, I don't actually kind of exactly know how this works, right? So what would be a sensible way of thinking about what does this function actually do? Well, the thing I'll probably do is I'll do something like this. I'll probably think that, okay, I know that x might be between minus 10 and 10. I'll make a grid of that. Theta is probably some angle, so I'll make that between 0 and 2 pi. And now I've got this 200 by 200 evaluation points. I'll run a big for loop around that whole thing, and I'll plot an image looking something like that, right? So now that image will start telling me something about, okay, it looks like there's like one peak value. I can maybe see something about the interaction between the two variables and so forth, right? Another thing you could do is you can plot the histogram of the output, right? And now that histogram would be able to tell you things such as, well, actually, for pretty much most, the ticks are gone on this one, but for pretty much most values, this is going to be very close to 0. It's pretty much this function, whatever I run with it, it returns quite small values, and then there's a long, big tail here, right? So that's a really useful thing to do, right? Because say that this function is a part of some code base that you have, and you don't actually know what people are going to put into this, right? You don't know the values that they're going to chuck into it, and you're going to use the output on the other side. Well, this histogram is a really, really useful thing to have there, right? Because you can actually represent the output of the function by this histogram, right? Cool. So that process that we just did now is actually something that we can think about as the concept of marginalization. So let's say, in this case, we have this function that I give an x and a theta, and it returned res, right? That is something that we can think of as a likelihood function. Now, the distribution of that here would be like a likelihood function. So I pick in an x and a theta, and I get an output value out. And then I have these two things which I'm integrating over, which in this case, which is picking all the values, chucking them through that function, I get something out on the outside. In this case, that was like saying that I have a uniform distribution over theta and x, because I just took a grid between minus 10 and 10 and 0 and 2 pi. Now let's say that you have a bit more knowledge, that you actually might know something that, you know, the values of pi or theta is actually not just uniform between this. I actually think most of these values are around pi or pi half. Then you can alter that, and this process will now tell you a different distribution over res, right? And now the notion of being able to treat something like this is really nice, because now I can treat a function or some object statistically instead. Instead of saying, I don't know what's coming into this function, but I have an idea of what the distribution of values that comes into this function. Now I get some distribution of output values. Well, cool, now I can go do the same loop again. They can go into the next function and so forth. And that's the idea of treating these things as statistical objects. And this is basically pretty much what machine learning is. So I'm going to give another example of what we can do to try and give some intuition of this object. So let's say that we take two of these simple linear models that we looked at. we take one which has a sign matrix which is X, so it has one beta, and then we have this other matrix that has a set of basis functions, 6 of them, which are going to be these bumps that we drew on 2 lectures ago. And then we're saying that we have a response variable, in this case, that's distributed as a Gaussian. Okay. So now, if I would take my linear model, so the first one, that means that each setting of beta is going to generate one of these, and my likelihood function over beta over y is going to look like one of these bars, right? And now I'm going to have a belief over beta that says that I think beta is close to 0. So it wiggles more like this. These ones are more likely than the others. So now if I do that integration, I'm going to end up with something like this. Right? Now I've effectively removed beta from this. This only depends on y. If I do this one instead, now I have these 6 basis functions. I still think they're close to 0. Then these are some of the functions that I can generate. And now if I do all of them, I do that integration, I get something that looks like this, right? So now if we look at these 2 objects, right, they look very, very different, right? They place probability mass in 2 different places, right? The line, I could just have the slope, it places probability mass out towards the boundaries, while this one places all its probability mass in the middle. So what we can now do is that if we now see some data, now we have some data, we can evaluate that under this distribution, and then we can start saying, well, actually, if I got data that moves around in the blue region here, it's going to be much higher probability under this model than under this model. So that's the notion of marginalization. So, and let's go back to where we came to this problem, and that was in the notion of doing dimensionality reduction or unsupervised learning. Remember, I had this notion where I said, okay, I'm here today, how did I get here, and which path did I take? I'm going to try and do a sketch to explain this a little bit more simply. So what we have is that we have some output data. Carl is here. And what we want to do now is that we want to get some input locations to each one of these output points. So we want to give them each an x, and we want to connect these x's with a function, right? That's the 2 things we want to do. So I think about it as an abacus, right? I'm going to slide these along here, and I'm going to give them each an x value, and then I'm going to connect them with a function, right? So that's a valid solution. That's a valid solution. That's a valid solution. I can keep going for quite a long time here, right? I can connect this with any kind of function. I can put them in any place I want, right? So now, what we said was that, think about this, right? That was like evaluating that function. That was like putting in an x value and a function, and then I could draw this thing, right? Now, what we want to do is that we want to say, you know what? I have a belief, or I have I have a specific representation that I like more than others, right? So say that I want to do a visualization of some data. I want the visualization to look in a specific way or pick up a characteristic in a specific way. Now that means I don't put in just any x. I put in the type of x's that I want, right? And I might put in the type of functions that I want, right? So that's placing in, use not any, but I pick a specific distribution of these. So that leads us to this marginalization object, where I would now say I have some preference over certain representations of the data. I have some preference on how I think, given these representations, because that's not the only function that goes through those points, right? there's a lot of functions that goes through those points, right? So I need to have a belief over both, right? And then if I have that, I have something that if I now put those through the function, I can generate the data. And now what I want to do is that I want to average out, I want to write this for loop over each of these. If I can do that, then I have this object P of y, so that thing that we saw, that those two distributions. And now what I can do is that I can simply do base rule, and I can get this object, which is the thing I really want. It's the object that says, here's your data. Now here is what I think now the x and the f should look like. Okay? So that means that integral that we had on the previous slide means that I need to test every possible function and every possible input location for that. That thing, that for loop that you need to write is very large, because the set of possible functions is possibly infinite. And if you formulate distributions over those, so you actually say, let's say that f and x for some reasons are Gaussians or something, even analytically, you wouldn't be able to do that math to solve that equation for most cases. So generally, this is something that's computationally intractable. And that's the thing that we're going to try to address today. So then just a couple of comments on this. This is Niels' house god, Simon Laplace, who apparently at one point in time said, nature laughs at the difficulties of integration. There's another thing with integration that is a nice XKCD schematic. So differentiation, this is something that you do. There's a set of rules. This is why neural networks are so popular, because they're not statistical models. They just work on differentiation. And differentiation, you can write code to do. Well, this is integration. Integration is an art form, nothing else. We don't know how to do this in this way. This has Bone calls the mathematician, burn the evidence. What the heck's a Bessel function? Well, integration is really, really hard, but it's a super, super, super important thing. And I have another very nice quote from Henning, Osborne, and Kirsting from a book that is not published yet, which says this: integration is a key step in inference, where it is encountered when averaging over the many states of the world consistent with observed data. Indeed, the provocative Bayesian view is that integration is the single challenge separating us from systems that fully automate statistics. More speculatively still, such systems may even exhibit artificial intelligence. And I think that quote says a lot of things about the authors, but I like the fact how disdainfully they use the word AI, because it's a terrible word that we should all stop using. And yeah, cool. So basically, if we could solve integration, possibly we could have self-driving cars in my lifetime or something like that. Integration, key thing. So that's what I said. You are going to see, so why are we talking about it in this course? Well, you're working on your projects now. It will be, as we said, it will be super unfair to start introducing things that you should actually submit on Wednesday. So what we're really doing, right, is that we're trying to give you a flavor of a couple of things that are going to become super important if you continue doing machine learning. So you will encounter integration tons of times, many courses, many projects after this. And it's very rarely analytically intractable. Most machine learning models, it's not. So you saw this thing, this number that Neil showed, that data science is 80% wrangling data, 20% building machine learning models. The 20% of building machine learning models is 3% coming up with a model, 17% coming up how you approximate that model, right? That's basically, or which is nearly always how you approximate an integral. Pretty much always what it is. Cool. So I'm going to show you another intractability. So if you kind of get the notion that I tried to say with the unsupervised learning, why that will be analytically intractable, I take a general distribution, I push it through a general function. Do you really think you can write up the math for the object that comes out on the other side? Most likely not. That's analytical intractability. We're going to do another one now. So I found this fellow on the internet. He has segmented himself from the background, right? So he's taken a photo, and then he wants to remove the background and just have a photo of himself, right? So cool. What is this? Well, this is like taking this data and then finding a binary mask that's foreground background, right? So what you effectively do if you would build a machine learning model for this is to take each pixel, associate each pixel with a binary variable, and then you would have an observed pixel. And now what you want to try and do is infer the binary representation of that pixel, right? So this is something called a Markov random field. So you have these observed pixels, and then you have a binary pixel that generated that, right? That's basically how this thing works. So let's just think of what we would need to do in order to solve that. So in order to do then base rule on this, we would have to compute this integral. So we might have some belief over what we think likely nice binary images are. Maybe there are things that have big blobs of foreground and background. Not every other pixel is foreground and background. So that we formulated some notion of that. So then we need to integrate that out here. Okay, so this is a discrete setting. So that integral is just a sum. So now, how big is n? N is summing over every binary image, right? So let's just look at how big n is. So that is an iPhone 3GS that was released in 2009, I believe. It had a 3 megapixel camera. Cameras are much higher resolution now, but you'll see why I picked this one. The number of binary images that you can generate, so the number n in that sum, is this. That's the number n in your for loop. Okay, so you got 2 to the power, very big number, black and white images, foreground, background. We always do this. Number of atoms in the universe, age of the universe in seconds. So you can just think this, you don't want to run this loop, basically, right? Cool, we got that. So even though this is completely tractable, you just take every binary image, you enumerate them, and then you just write the for loop. You can't do this. So this is something which we call computational intractability. So we got these two, computational intractability. There's simply too many states to sum over. Can't do this. This happens super quickly. You're computer scientists, you know about combinatorial explosion. This is happens straight away, right? The other things is analytical intractability. Use stuff where there's no closed form, there's no mathematical form to write down what the integral is. It appears straight away in this unsupervised learning scenario that we talked about. Yeah, great. So what I'm going to do now then today is to just hint at 2 different ways of dealing with this problem. So how can we look at integration from 2 different means? How can we look at it by thinking about statistical methods, and how can we look at it from a deterministic point of view? Great. Do we have any questions so far before I go? Yeah, shoot.
Is PCA not analytical?
So it's actually the maximum likelihood solution to it. So it's a bit of a weird one, because if you want to have a prior over both W and X, it's intractable. But what you normally do is you integrate out one of them, and then you pick the maximum likelihood, which is called a type 2 maximum likelihood, to the other. Cool. So stochastic methods does something like this. So I have this integral that I want to compute. So f of x, p of x. So I want to find the expected value of the function f under the distribution p of x. So now what you can do, like first thing anyone will do, is to say, great, what I'm going to do is that I'm just going to draw samples from p of x, and then I'm just going to take an average of that, right? Okay, if you do that, if you take infinitely many samples, it's fine, you're doing the right thing. So that means the thing you need to do in this case is you need to draw samples from a distribution. And this is something, how do you actually draw samples from a distribution? Do we know how to do that? Like we know how to call np.random.randn, but how does that actually work? Yeah, so the way it works is this. Okay, so let's assume that you can draw uniform random numbers in a computer. Let's assume that. You can't, but let's assume that you could, right? We can have decent approximations to randomness, at least. And then I have this red distribution that I want to draw a sample from. Yeah. Now I have the mathematical form for that. So what I can write up is the cumulative distribution of that, which is the blue one. Yeah. So the blue one's now going to go from 0 to 1, right? Accumulation of this distribution. Now, if I draw a sample uniformly between 0 and 1, so my random uniform number between 0 and 1 on this axis, and then I push that dunk, dunk, through the cumulative inverse of the cumulative distribution. Now you can see where the cumulative distribution has a very sharp edge, right? Where the gradient becomes really high, that means I have probability mass, right? It counts up very quickly. So that means I'm going to get a lot of values here. Where it's very flat, there's a very small range of y values that's going to give me a large range of x values. So I'm going to get little mass here. That's how you draw from a distribution. But as long as I have a means of drawing uniform random numbers, and I can write down the distribution so that I can write down the cumulatives, I have the mathematical form for this, I'm fine. We can do this. Okay? But let's say that I don't know the mathematical form for the distribution itself. Right? So I don't. I have something that I can evaluate, but I can't actually write down, I don't have the mathematical form for me. Can we still draw samples from this? And I'm going to show you two ways of how you can do that. The first one's called rejection sampling, and the other one is called importance sampling. Great. So the notion of a rejection sampler is this. So I have this red one, the same one we're going to do throughout the lecture. I have this one. Now what I'm going to formulate, I'm going to pick a blue distribution that is guaranteed to always be above the red distribution. Okay? And then what I'm going to do is that I'm going to draw, through the process we had before, a sample from the blue one. Now it turns out I drew this one here. And then what I want to do now is that I want to correct for that gap, right? So what I'm now going to do is that I'm going to rescale the value from here up to the blue line and make that 0, 1. And now I'm going to draw a uniform value along that line. If that value ends up being there, I reject. If it's down here, I accept. If I do this continuously, that means I'm going to draw a lot of samples here, and I'm going to reject everything. That means I'm actually eventually going to draw from the red distribution.
The one you mentioned, blue distribution, since it's always above, it has to be the blue line, isn't it? Distribution.
No, very good. Very good.
Can I go to the top of the club?
Yeah, you can. Neil's absolutely right. So of course it's not a distribution, but what we have is that I have a scale distribution.
Why am I saying it's not a distribution? Someone say why I'm saying that. Because it has to be greater than 1.
Exactly. Very good. Neil gets an apple after that. Exactly. So what you generally do is that you would, of course, right, if those two distributions were the same, I accept every sample, right? So what you would pick something simple, a distribution, and then you will multiply that with a value to push it above, right? And now, if that value is very large, you know that you're going to have a lot of empty space. So you're going to have a very inefficient sampler, because it's effectively, if this thing sums to 512, you know that this sums to 1. Well, there's 511 of white stuff in between that I'm going to reject, right? Cool. This is generally very easy to do and very, very inefficient in most cases. I don't actually know where rejection sampling is often used.
I guess it's used in statistical reweighting. Sometimes where it's saying everything Carl's saying, of course, is much worse in high dimensions. So it could, in one dimension that would be fine, even if it's 500, because 500 samples for every one probably not bad. But when you go up to high dimensions, that amount of space starts to explode exponentially, and you just never hit.
True.
I think, yeah, probably use quite, it's a cool trick for like this.
Cool.
It's just not used in high dimensions.
Yeah.
And a lot of the Bayesian stuff I was talking about high dimension. But if you're in one dimension, yeah.
So the other thing, so effectively the previous one is super inefficient, right? As Neil said. So because we are throwing away a lot. So the next step to fix this a little bit better is to say, let's say that we could reweight the values of the samples. And we can do that really, really simply through a procedure called importance sampling. So what you do now is that this is the thing that we want to compute. Remember, P of X, we don't necessarily have, we can evaluate it. What we can do, we can just add another distribution, in this case Q, to this expectation. It doesn't do anything. And then what we can do is we can rewrite this such as this instead. And now we can think about this as an expectation or an integral over Q instead of an expectation over P. So what we can now do is we can draw samples from Q and reweight them based on this, right? So we can think about it as this instead. So let's see the image of how that will work. So now I've lowered this one because now it is actually a distribution. And now you can think of the relevance factor I had here was P over Q. So now I draw samples from Q. In this region here, I'm not going to get very many samples from the blue one because the blue one has quite a low probability here. And then what I'm doing is that I take P over Q, which is value higher than 1. And now I'm going to upscale those values. While over here, I'm going to get much more samples from the blue one than I should get. So now I down value them, right? So you continuously use the ratio between the two districts. And this is something called importance sampling. So you effectively have a weight associated with each sample, and then you rescale for them. Great. So the last thing, which is really the first thing, well, we'll come to the first thing one should often do before one goes crazy, is formulating something which is called a Markov chain Monte Carlo. And generally, there's something that we're going to talk briefly about, which is a Git sampler. This is really the first thing when you have a model that's intractable, that's super useful and super easy to formulate. That image segmentation example, I would solve with a Gibbs sampler. That's super easy to write down. We're going to see why. So the notion of a Markov chain Monte Carlo is this. So instead of doing what we did before, we said, I'm just going to draw samples from one distribution independently, and then I do something with them. Can we have a sense that if I draw a sample here, the next sample is related to where I drew the previous sample? So I formulate a chain of things, right, instead. So now you can start thinking about notions of explorations of something in this case. So you remember the state that you drew from previously. So you start off with some form of state. So I draw a sample and I have some form of state x0. Then what I do is that I have this proposal distribution that I can draw samples from. That's conditional. So that says now I'm going to draw a new place x star. And then what you do is you want to be able to do some form of exploration exploitation trade-off. So now you want to say, should I accept this new state? And what you do is you compute an acceptance probability, which is the ratio of the probability where you were before and the probability of the new value. So now you can see that if you move into a region which is much, much less probable, so x star is something that has a really, really small probability according to p, then you will say, now it's a small chance that I'll accept it, but I keep a chance to accept it, because it might be the case that I go to something that's really bad, but then from that state, the next step, I move to something that's really good, right? So you have, like, think of having two bumps like this, and you're in one bump, and you just want to draw samples here, you get high probability all the time, this is exactly the stuff that you want, but then you will never reach this one. So sometimes you need to do something bad to do something better. And this is what's called a Markov chain. So you then can just do this. So if you have that acceptance probability, you just draw a uniform number between 0 and u, and then you accept this sample if it's higher than that probability. Cool. So the thing that I wanted to say, or that I started off saying, which is the thing, if you have a probabilistic model, you can usually write a very, very, very simple Markov chain, which is called a Gibbs sampler. And these ones are super, super simple to write, because now your proposal distribution is that you have a set of variables, tons of variables, like all the labels for each pixel. Now I fix one pixel, and the conditional distribution is knowing all variables except for one. And then I draw a sample over that, and then I keep going. So you sample each variable in turn, and then you cycle through them. So look at this one. So I start off with x0. Now I pick a variable from my set of variables, and then I formulate the posterior distribution over everything I assume that x not I have the value of, and then I draw a sample from x over xi. So what does the way to think about this? If I know everything except for one, if all these people had to vote for that one, what do they think that one would be? I draw that, and then I sample from this, I get this new point, and then I chuck that back in to the previous, I now pick a new I, and then I keep going. So why is that much, much easier to do? So this was the thing that we said that we needed to compute in the image segmentation example, where this n was just horrifically big. However, if we change it to become this instead. This thing where we said, I'm just looking at one variable at the time, this distribution is actually really, really easy to formulate. So now, in order to get that distribution, instead of integrating out at the bottom here, summing over all possible binary images, this distribution, we just sum over all possible images by changing one pixel. So if that's binary, as we had in the case above, to compute this one, that's integrating over the value of just one of them, the only thing we have to do is a sum over two, right? In this case, if this is foreground and this is background, I just pick two of them. It's super simple to do this. And this thing, you can solve that image segmentation actually really, really well. So, you could take a whole course on sampling. There are, well, you can do a PhD on sampling if you want to. This is loads of stuff in here. The notion that you just get to know or think about is that it's basically some form of numerical method where in the end, you're trying to convert an integral to a sum. And now you're trying to come up with a way of summing the relevant objects. So you make the n in that sum as small as possible, right? You have guarantees that if n goes to infinity, you're doing the right thing. You know that. But infinity is a very long way away, right? So all these methods are basically super useful for specific cases. And what I think, though, is that Gibbs samplers, as I said, this is often the first line of attack of something. So you have some form of likelihood function, you have some form of function itself, and you want to figure it out. Well, you do something like this, and you can get something out quite quickly. You write some form of for loop around it to test lots of things, and you get some statistics out on the outside. Cool. So,
I can say, I was thinking while I was doing the introduction, it's an enormous amount of work done on these sampling methods, as Carl just implied. And in fact, one of my PhD students, Francisco, was just produced a new sampling method, which looks very good. And I think if you are, there's a lot of maths in it as well, and the maths get really, really mathematical very, very quickly. And I was trying to think why that is. Number one, they are incredibly useful. I mean, of all the things you can sample from in the world, right? Like if you're trying to describe something as a probability distribution, you then want to sample from it, right? And actually the thing we can do that for versus the complexity of the world is a relatively small fraction. But there's still a lot of stuff in there. And then I think the reason why it's such a sort of fertile ground and interesting place to work is that the maths can get quite complicated quite quickly while still remaining useful. You know, so there's a lot of things where you can just make the maths very complicated very, very quickly. And you stumble across fields of pure maths when you're doing this type of sampling because of the things you need to prove to what you're doing. You know, these areas that people thought weren't going to be useful, just because you can get quite creative about how you form your sampler. And I think that's why it's, I mean, it's a useful area. It's probably got more people working in it than its utility. But it's really, if you, like, we've gone quite a non-mathematical dead science course here. But if you really are into maths and like this sort of stuff, doing sampling, I think it's a really interesting direction.
Yeah, it's a tricky thing because I think where the gap is on the third point here, is that if you know something about the problem domain, you can improve your sampler massively. But most people who work in sampling work at it as an abstract concept. And sometimes we get these things where, cool, we've shown all these weird things, that's super nice, these nice asymptotical behaviors for certain things. But then it happens to know that I'm working with data from a sheep farm. Well, great, now I can just take that knowledge and, you know, you don't have to do this. And then, so it's a tricky thing.
And a good example of that, I mean, not good morally, but a good, so the Metropolis Hastings algorithm, which by all accounts is invented across the 50s and 70s. If you look at when Metropolis and Hastings published, was actually developed for doing the calculations behind hydrogen bombs. Not the initial atomic bomb, but the complex integrals you require to do hydrogen bombs. You know, in secret in Los Alamos, in probably initially. And so there you see that a lot in physics. So physicists are really good at the sampling methods because they're often working on these quite complex real-world systems where you have to resort to sampling, and they tend to be very mathematical. So you often see that marriage, and a lot of the people who work on sampling methods and machine learning come from a background of physics.
Yeah. No, that's absolutely true. That's exactly what yeah, we were doing some stuff. Actually, the things that I'm going to bring in now, talking about doing deterministic approximations to this with some people studying gravitational waves, and they had these samplers where they basically had to, I don't know, simulate the universe, right? And then they were like, oh, how can we do this? And they each sample took an enormous time to do, and they had, yeah, it was very complicated stuff. Cool. So the other approach, I'll have to be much, I'll skip all the derivations because we don't have time for that, but they're all in the slides. So the other approach is, if we know that these stochastic algorithms, if n goes to infinity, we're fine. But infinity, as we said, is big. Can we instead say we're never going to be fine, but we're going to find a rough estimate of something? And that's what we call the deterministic approach instead. I usually think of these two approaches as the superheroes of machine learning. And we've got MCMC man. MCMC man is like very correct, and he works in the limits and takes forever. But when he finds the criminal, you know that it's the right thing. And then you've got variational Bayes woman, and she's like, she shoots first and asks questions later, but she gets the job done, right? And the thing that we're going to talk about now is to talk about.
I was wondering about the gender stereotype.
My gender stereotype.
The other way around, but yeah, no, it's right.
But it was because I found images of them that suited really well. So what we're going to try and do is, let's look at this as a graphical, model. So we formulated this model where we say we've got some x generating some y, and what we want to do is we want to integrate out the y. So we want to reach this thing. If we reach this thing, we can also get this thing, right? That was just, if we have this, we can generate this through Bayes rule. So if we write that integral up, this was the thing that we were working on, and we said we can't compute this. So there's another way of writing this object, and that is just writing Bayes rule in an odd way. So normally you would have this as your denominator, right? But we can write Bayes rule like this instead, right? Okay, nothing strange about that. So effectively, this object and this object, if I find one, I can find the other. So instead of looking for this one, we're going to look for this object now. So we're going to look for the posterior directly, and by looking for the posterior, we're effectively going to find this as well. Okay? So the way we're going to do this is we are going to say we're going to pick a distribution Q that is going to approximate this one. And this distribution Q are going to have some parameters theta, and we're going to say that theta is going to embody all information that y has, so I don't need y. Okay? So effectively, if we draw that as a schematic, we're going to say we're going to take this model here, where x is informed by y, and say, now x is informed by theta, such that I don't need y. Okay? If that's true, well, fine, now I got this, and that effectively means I got this. Right? That's the notion that we're going to do. However, this is never ever going to work, right? Exactly. Because what I started off saying was that if this is analytically intractable, then I'm saying the math that could write this down doesn't exist. Okay, so if this math exists, well, then this math doesn't necessarily need to exist either, because if I divide something with each other and get something that doesn't exist, that probably means this doesn't exist, right? So clearly, if I write down an approximation or a form, mathematical form of this, well, it's not going to be exact ever, right? So that's the idea. Okay, we happy about that? Cool. So I have 5 minutes. So what I'm going to do is that I'm going to be, oh, let's see if we're going to do with this. Can't do the whole derivation. What we're going to do, as you see, can't do that, can't do that, can't do that. We're going to be very quick. Exactly. Exactly. So what we're going to do, well, you can look through that. They're very verbose. So what we're doing exactly is that we are going to write down. Hopefully, if you look through it, you were very quick to read. What I did on the previous slide was that I wrote the top line of this. I wrote the top line of this, and what that line is basically my Q, so which is my approximation, P of x comma y, which is the joint distribution that you can always formulate if you've got a likelihood and a prior, because the Q's comes from multiplication. And then we've got this last term here. This last term here is the thing that contains the object that we wanted to approximate, but that we don't have. So the last part of this integral is actually, or the last integral there, is the thing that contains the intractability that we have, the thing that we wanted to approximate. Now, what I showed previously in the couple of slides was that that object there is always positive. It's not very hard to show that it's always positive, and I could do that. It's always positive, and it's equal to 0 if Q of x is equal to P of x given y. And because of that, I can now say that the remaining terms is actually a lower bound on this. And if I now, because Q is the thing that I wanted to learn, so if I now do an optimization and I make this term, these two terms, as large as possible, that means I'm necessarily making that term smaller. And because I'm making that smaller, I'm pushing Q towards the distribution that I wanted. The schematic of that is this. So I have this thing, which is what we wanted. I formulated that as two terms, one that's not computable, which is that the last integral, the one I dropped, but I know that that one's positive. And then I have this term here, which I can compute. If I now make this as large as possible, I'm necessarily minimizing that thing. And that's what's called an evidence lower bound. That went super quickly, but hopefully you got the notion of that. So I turn this into an optimization problem. Very, very rarely the KL divergence is going to be 0. Right? It's not, because if it was 0, I could compute this integral by hand. Right? Cool. So, key thing is that this thing is never exact, but you can do this very, very fast, very often, because you're allowed to choose the quality of your approximation. And this is very, very useful. So, as I said, shoot first and ask questions later sometimes captures the wrong criminal, right? But gets the job done. Cool. So, just a very brief summary of what I tried to get across today was this: why is integration a key aspect of machine learning or of data science? Is this notion, think back of that object of code. So you have something that you don't know exactly what it does. Well, what do you want to do with it? Well, what you start off first is you just throw values at it. Right? You throw as much values as you can at it, compute, and see what gets out on the outside. Well, the best way to parameterize this is by a distribution. So now you say, oh, I actually think most values that will come in will be between 5 and 10. Cool, so I place a distribution of those values. Now I run the code and run the code and run the code. Now that leads to a distribution of output values. Now what that means is effectively you're doing an integration. You're taking in an input distribution, you integrate it through your function, get an output distribution. That allows you to study things statistically, right? Rather than putting one value in and see what that value, you do it for the whole thing. Now, integration for these bigger things becomes intractable. Well, it doesn't need to be big. It becomes intractable straight away, which forces us to do this approximatively. So this was used 2 ways that you can now have in the back of your head when you take further units in machine learning. Now, the last thing that I wanted to mention is that, remember when we talked in my first lecture about the no free lunch and things like this, right? How can you interpret solutions? Now we added another complexity to this thing. So even if my notion was that I said you can only ever interpret your solution in the light of what you put into it. Now I've made it even worse, because now I'm adding another level to it where I said, yeah, I put this in, but I couldn't do the math, so I also approximated it. This is a really big thing as well, right? So often you see very nice models that we use sit and interpret the models themselves, but you also have to interpret how these models have been fitted, because they nearly always have been done using some form of approximate methods on this. Cool, and with that, I'm gonna end. Cool, shoot.
There's a practical for you.
Yes.
So I think what we'll want to do for practical 4 on Tuesday is you submit the state of your notebook from the assignment as it is, and in the ticks, what you're going to be asked to do. So if you want to, by practical 4 on Tuesday, have your code working such that you'll be able to make predictions of house prices for given locations, right? So you've got that bit in part 3, and then so you're going to want to be able to do that on the ticks for practical for Tuesday. But then you'll get a chance to refactor because the hand is like the next day, right?
Right.
Is it Friday? Yeah, Wednesday, last day of term.
Or did we get till Friday? It's Friday. Okay,
So
we got
yeah,
all the way
so
till
you
Friday.
just basically want to get, so you want to be able to show a practical 2 that you've gone through the process as much as you can and try and make those predictions, and also be able to talk through. It's a chance as well to talk through your assess work as well. And it's really trying to get you to make sure you've got made significant progress on the assignment, because you're not going to be able to do it like the last minute. And get some support on that. So that's what the tick is on Tuesday. Yeah. Okay.
Cool. Oh.